Adelante.
Okay. So welcome everyone. Welcome to this new seminar from the Institute of Physics of Andalucía in Spain, in Granada. Today is our pleasure to have with us Carlos Carrasco, or Charlie, for everyone who knows him. He's visiting us for a few weeks as a friend of the virtual project, and he will be talking today about dust in protoplanetary disk. So Charlie made a bachelor in physics at the University of La Laguna in 2004. And he made a PhD here at the EA, working on the topic high angular resolution study of jets and disk at the earliest stages of star formation. He finished in 2010. Then he made a 3 years postdoc at the Max Planck Institute for Astronomy in Bonn, working with the submillimeter group, working in a survey at radio wavelengths of the whole galactic plane with the very large array. Then he moved to Mexico. He's the staff researcher at the Instituto de Radioastronomía y Astrofísica, the IDEA, of the Universidad Nacional Autónoma de México in Morelia. He's investigador, the equivalent to the investigador científico at CSIC. Then he, in addition to making research, he is currently the chief of the computer department at the IDEA. And his expertise is in radioastronomy, both interferometry, but also single-disk radioastronomy. His research is focused on the study of jets and disk, with contributions in the field of protostellar jets, the launching and collimation mechanisms, and the role of magnetic field. And he's also involved in the study of disk evolution and planet formation, in particular, what he will be talking about today, the characterization of dust properties in protoplanetary disk. And also he's involved in radioastronomy instrumentation projects, and he's the head of the Mexican participation in the next generation VLA. Okay, so today he will be talking about that in protoplanetary disk, still that we can know. So the floor is yours.
Thank you very much. I'm happy to be here. It's not too much that I come back to Granada since I finished my PhD. So I'm going to talk about I'm trying to give a summary of what we have learned and what we have unlearned from high angular resolution observation from ALMA. ALMA started to observe protoplanetary disk with high resolution 10 years ago, and there is a lot of things we have seen from this data. I always start with this. Planets are a side effect of star formation. If this is the common picture we always talk about star formation. At the beginning, you have a protostar accreting. At the beginning, the accretion is spherical, but then a disk is formed in the equatorial of the protostar, and most of the accretion is through the disk. And we also have bipolar winds, jets, and outflows at the early stages of the star formation, but at the end, from 1 million years approximately, accretion stops, winds stops, and the disk and the rest of the disk evolve to form planetary systems. So in this picture, actually, every star should have planets around, because the planets are just the remainings of the accretion disk. These protoplanetary disks are made of gas and dust, more gas than dust, 90% of gas, 10% of dust. The gas is supposed to be accreted or launched from the protostar in winds, and the dust is going to evolve to form planets. How is this happening is the question here. The dust should grow, and should grow a lot to form planets. We start with this. This is what we have in the interstellar medium, is dust particles less than 1 micron in size. And we need to form first this. And we know that this is already present in 1 megayear protoplanetary disk, is pebbles, something we call pebbles. It's small rocks of between 1 millimeter and several centimeters. We know that this, we think that this should happen because of dust coagulation. Dust coagulation is basically you have several dust grains of small dust grain, and all of them shocks, and then start to grow to form bigger things. We don't know how, but in some way this should give rise to these planetesimals, which are rocks of 0.1 to 100 of kilometers. And then this is going to be the building blocks of the terrestrial planets and the core of the rocky planets. This is how we think is planet formation is going to take place in protoplanetary disk. Also, several things we are seeing now with ALMA say that maybe some difference could happen. We don't know how we pass from this to this. Oh, this is not working very well. So the dust moves in the disk. We have a lot of gas, and the gas is what dominates the kinematics in the disk. So the dust basically follow the gas and follow the gas in different ways. The small grains, 2 millimeter grains, because remains coupled to the gas. So they are everywhere, they are floating in the gas, but the larger particles are affected by drag forces. So they go where we have higher pressure in the gas. And for example, the first thing that happens in a disk is that all the large particles, when they grow, they go to the midplane. And this is the setting of the vertical setting. And we have also radial drift. When we have big particles, they interact with the gas and they lose angular momentum, and they go to the higher pressure places in the gas. So they go to the center of the disk, or they go to other places. We will see something like that. And this is called radial drift. And the problem with that is that finally the gas, the dust could fall into the star and become part of the protostar. So we lose dust. The question is, can we form planets before this happens? And this is this has been the most important theoretical work, because what models of dust fragmentation and drift or radial drift of the dust say is that we cannot form something which is bigger than 10 centimeters in the disk. When we have something which is 1 centimeter, they start to the velocity of the shocks between the dust grains are more optimal for fragmentation than growth of the dust. So we have this limit, 10 centimeter. And then from pebbles to planetesimal, we have to have, we need a different mechanism. We still don't know which is. But in order to study this, in order to study which is the mechanism that to form planetesimals, we need to characterize the dust properties in this. And this has been very difficult before ALMA. This is the typical, spectral energy distribution of a protoplanetary disk. And as you can say, you have the peak of the emission at the submillimeter. This is the optically thin part, and this is in the millimeter and centimeter wavelength range. But we need a lot of angular resolution, because this is like 100 astronomical units in size. So we need to study the regions of the dust where the dust is accumulated and the dust could grow. And this means that we need angular resolutions of the order of 1 astronomical unit. This is like 10 milliards seconds. And observing in the millimeter with 10 milliards seconds inside thermal emission has not been possible since ALMA, until ALMA. So this is why we build ALMA, but we also have the very large array. And the very large array observed in this part, in the longer wavelength. And actually the VLA was the first instrument able to resolve millimeter emission in this at 7 millimeters. We have ALMA. I already mentioned this. ALMA is the most powerful millimeter interferometer we have ever had, and it has completely changed our vision of protoplanetary disks. These are the wavelength range that can observe ALMA and VLA. ALMA can observe, in principle, optically thin and bright emission from the dust, and VLA can observe optically thinner but much weaker emission from the disk. And you have to take also in mind that dust transparency goes in this way. So a longer wavelength we have more dust transparency. So I want to show you how we have evolved in observation of this. This is what we were doing in the 90s. This is HL Tau, HD169142, and TW Hydra. They are three very famous, these very bright disks. And 1 million years, 5 million years, 10 million years, these are all VLA images. VLA was the only instrument in the 90s able to resolve emission from a protoplanetary disk. These are not very impressive, They don't look like this. Almost they don't look like this. But we were able to put some constraints on the size of the disk and constraints on the mass of the disk. This was the 90s. This is what we were doing in 2000. This is from Karma, a millimeter observatory which is not anymore working. This is from VLA, but after an update of the detectors of the VLA, so there was an improvement in the sensitivity. So we could observe a millimeter wavelength at higher resolution. This is from 2 millimeter array. So now at least they look like this, no? They look like circles, resolved disco. This is the beam size, for example, in HL tau. These are the same disk. This is what we do now. This is ALMA. And this is totally a giant step because we are now studying a lot of different scales, and you can see that we can now resolve a lot of substructures in the disk. And this is probably the most important result from ALMA. What ALMA observation of protoplanetary disks have teach us is the most important lesson is rings and gaps. This was the first image of a protoplanetary disk with the highest angular resolution. With ALMA, this is what 1.3 millimeter. This is HL tau. Is one of the brightest protoplanetary disks in the sky. It's very massive. It's supposed to give rise to a 1 solar mass star. And the most important characteristic in these images was the bright rings and the dark rings. We know now that bright rings are related with dense dust rings. So the dust is accumulated in these concentric structures, which are very dense. And these dark rings, these dark bands are related to low density regions in the disk, low density of dust. So these are called typically gaps. I'm gonna talk about rings and gaps in the following, no? And this was very impressive because we never saw multiple concentric substructures in this before this image. This was a couple of years later. This is TW Hydra. It's 10 million years. It's the same. It's going to give rise to 1 solar mass star. And it also showed substructures, but some kind of different substructure, more wide rings and more narrow gaps. This was other images. I want to take your attention on this. All of them show concentric substructure, but this is very interesting. In blue is the gas, and in white or pink is the dust. So you can see that the disk in gas actually is very big, and all the dust is concentrated at the center. This is because of radial drift, and this disk has also spiral arms. And spiral arms are considered a proof that you already have planets there. No, this is the DSHARP project. It was the first survey, a blind survey of a sample of protoplanetary disks. We didn't know anything about the structure. We just it was selected and see what happened when we see them at higher angular resolution, and all of them showed substructure. And this was a surprise. We were not expecting. We were expecting substructure, but not so common substructures in protoplanetary disks. So this was the first lesson, and this is a simulation. Sorry, I need to stop this. What I'm gonna show here is a simulation of how the dust grains in the disk evolve with the gas. So the simulation is in the gas, but you are gonna see the movement of the dust grains, and dust grains of different sizes. The black ones are very small and they are coupled with the gas. The green ones are a little bit bigger, so they are also coupled in the gas, but they move a little bit. And the yellow ones are the biggest, and particles of 1 millimeter or 1 centimeter. And what you see is that because of the radial drift, all the large particles go very fast to the center, and you lose them in the star. But then a gap is going to form there because complicated mechanism, but the important thing is that we are going to form a gap here. And then what happened with the gaps is that the gap stops migration. So particles don't pass the gap, and they can be accumulated here. So this is a natural way to stop migration, and then you have a lot of large particles there, and they can grow. because you will not lose them anymore. So this was very important because we thought that this structure were possible in protoplanetary disks, but we thought that they were not so common. So this gives us a natural solution for the growth of dust to form planetesimals. Now, how we form this substructures? So the most common way, the most easy ways to explain this is because we have already an accreting planet. So if we have an accreted planet in the disk, it will interact with the gas, it will interact with the dust, and it will make all these substructures. You have here rings and gas. But this is a problem because the best way we have to form planets, to form planetesimals, is in the rings that are formed by a planet. So this is a loop, no? So are all the substructures created by planets? So some of them they are, and this is one example. This is probably the best example. It's the only protoplanet we have directly detected. This is a circumplanetary disk in a big gap in this, but it's the only one we have detected. We have not detected any more protoplanets. But it's very difficult. I mean, this is a special one because we think that this is very massive. So it's not easy with the actual instrumentation to detect protoplanets because they are very weak. But some of them we have detected. So this is what I mentioned. If we need planets to form rings, to form protoplanets, this is a loop reasoning. So we started to propose different mechanisms to form rings, to accumulate dust in rings in order to have like an initial stage for the formation of the first planet. And the best and one of the most promising is the snow lines. Is that growth at the ice lines. And I'm going to try to explain this. This is a star and this is a disk, and the disk is hot because the radiation from the star hit the disk. So the disk is very hot here near the star and is cold at the external orbit. So there is a place in the disk where you have 0 degrees, where you have the temperature where the water, for example, where one molecule pass from a solid to gas. So you have solid water here, you have ice here, and you have water vapor inside the ice line. So you have a lot of dust grains. And dust grains outside the ice line will have ice in their surface. If there is water, they will have ice in their surface. And the ice is supposed to be sticky. So when they shock, they are more frequently, they are more commonly going to grow. If you don't have ice, it's most probably to fragment. So you have large particles outside the ice line, which can grow, and they will move very faster than the small particles. So they will go, and when they arrive to the water ice line, they lose the ice, and they have water vapor. So they will be slower because they are very small. They couple again with the gas, and they will move slower. So at the end, you have an accumulation here of small particles within the ice line, and this will create a reaction to the gas because this creates a reaction to the gas that will form a maximum pressure here just before the ice line. So you have an accumulation of large particles with ice there. So this will look like a ring, and then you have a place where you can form, when you can grow the dust, and you can grow the dust with ice, so you will form planetesimals with water. So this is very nice, no? So this is one of the most promising mechanisms to form the initial stages of rocky planets. So what we do is to observe at several wavelengths in order to, with higher angular resolution possible, in order to characterize the dust properties of protoplanetary disks, and then try to study, then to relate how is this going to grow to form planetesimals. But there is one of the most important problems is that because dust is accumulated in substructures, we have highly optically thick regions. So we were thinking that this was gonna be very easy with ALMA because you observe a one or two wavelengths at the millimeter, but no, it's a more complicated problem because you need a lot of wavelength in order to obtain the dust properties. So this is what we do. We made this study, for example, in HL tau, and when you have 4 wavelengths, very high quality observation. This is VLA 0.9, 1.3, 2.1, and this is from the VLA. Actually, it's a very deep observation with the VLA at 8 millimeter. So from this, you are able to get this. With some modeling, you can use different radiative transfer model or more simple models. But the thing is that from this, you can get the dust temperature, the dust density, and the maximum particle size. So you can see where are the highest density regions and where are the biggest particle located in the ring. And here, if you look, you see like that here are seven astronomical units where everyone says that there is probably a planet, that this big gap is a consequence of a protoplanet already accreting. We have like a minimum in the particle size, and this is what you expect when you have a protoplanet. But we also noted that here, these are the ice lines expected from this dust temperature profile. You have the water ice lines, the methanol, and the ammonia. You see that some substratus in the center, which are not so there is not so much contrast between rings and gaps, are actually related with the position of the ice lines. So this probably is a good example of a disk that already have a planet, but already is also accumulating dust in the ice lines. And the most important result from this is millimeter-sized particle. This is the first time we put a constraint on the size with detailed observations of the spectrum at the millimeter. And we said, okay, this disk, which is 1 million years, has already grown the dust up to millimeter-sized particles. And this is supposed, and this is what we need to start to form planets for other mechanisms. This is a more recent result. This is polarization from HL tau, this is the highest angular resolution observation of polarization in a disk. This is complicated. I'm going to talk about polarization at the end, but for the moment, what you need to know is that we have a different pattern of polarization in the gaps than in the rings. In the gaps is circular, and in the rings is parallel to the minor axis of the jets. And this means that there is a completely different mechanism of polarization in the gaps and in the rings. And the only way to explain this is because rings are optically thick and gaps are optically thin. And when you pass from optically thick to optically thin, you change the mechanism of polarization. And we have modeled this. And the interesting thing here is that this is the optical depth. Ignore this. This is the important one. This is the radiance in the major axis, and this is the optical depth. And you have 10 times more optical depth in the rings than in the gaps. So this means that 90%, at least 90% of the mass of the dust is stored in the rings, and they are optically thick. So this is a big problem because we were thinking that at 1 millimeter we have a optically thin emission, but actually, no. Actually, because of the dust is stored in very dense regions, it is optically thick. So it is very difficult to obtain important parameters like the mass. We don't know the mass. We don't know the mass of dust we have in these rings. This is a big problem. And for this, in order to solve this, you need to go to longer wavelength. You need to go to the VLA again. So, for example, you see these two disks, HL tau, GMR. These are 1 millimeter observation of ALMA, and you see here that the rings look very homogeneous of 1 millimeter. When you look at 7 millimeter or 9 millimeter, you start to see substructure within the substructure. You start to see substructure within the rings. Is this one? And we think that these are probably initial stages of planet formation. These are accumulations within the rings. You expect this, we were expecting this from simulations to start to see these clamps, dense clamps. But the problem is that you need to go to longer wavelengths in order to see this, because at 1 millimeter with ALMA, you are still optically thick. You are not able to penetrate this. There is a problem here is that the VLA is not very good. The VLA is the most powerful interferometer at centimeter wavelength, but this is very weak, and we need more image fidelity. And this is one of the reasons we want the next generation VLA to have more antennas and to be sure that some of them are noise or some of them are clamps. This is a more recent result. This is observation at higher frequencies. Not only at long wavelength we obtain information, it's also very important to observe at higher frequencies with ALMA. ALMA was built in Chile, in Atacama, at 5,000 meters to observe at this wavelength, not at 1 millimeter. You can observe 1 millimeter from California or from New Mexico. ALMA is in a mountain because we need to observe at this wavelength, and these wavelengths are necessary to go very high. People is not observing at this wavelength because emission is very optically thick in this. But you have some advantages with it. If it is optically thick, it means that it traces very well the temperature of the dust and also the albedo. And the albedo is related with the dust properties. You can also, it's the only way to see smaller particles. As particles around a couple of tens of microns. At millimeters, you don't see these particles. And it also allows to get the highest angular resolution with ALMA, which is 10 milliardsecond, which give us like a 1 astronomical unit angular resolution. These are the highest angular resolution observations at band 9, 450 microns. Of HL tau, and you can see increasing high angular resolution, and this is the center of the disk. And something interesting, there are two interesting results here. We see small particles within the gaps that looks very empty at longer wavelengths. You see very empty gaps, which means that there are no big particles, but there are small particles in the gaps. You can see here in black, and this is the gaps for comparison. And there is another thing. This is the snow lines, and we see an increase of the brightness temperature, and this is probably related with an increase in the density of particles, small particles within the ice line, which is what I was discussing before. Is the ice lines is the solution to this problem? No, unfortunately, no. There is no clear correlation between all the substructures we have seen in several disks with the location of the snowlines. So this does not mean that you cannot form planets at the ice lines, but at least in most of the disks we have seen substructure. There should be already formed planets. It is impossible to explain these substructures without planets. No, you cannot form these gaps only with the action of ice lines. You need planets. So this means that we have planets at 1 million years, and we don't know how to form them because dust growth is very slow. I'm going to talk a little bit about this, and it is extended compact disk, and this is a second result from ALMA, which is clear. We started when we started to observe with ALMA with high angular resolution. We started to see a lot of this with substructures like this. This is a survey of Taurus, and all these show substructures. But the thing is, we were not publishing. Actually, we're not publishing the boring disks, which are all of these. These are compact disks, okay, and they are more frequent. Indeed, they are the most. These are the most frequent disks. Now we have around 700 disks observed with ALMA at high angular resolution, and this was a nice study of all of them. And you see here that 30% are large disks with a radius of around 100 astronomical units, and they show substructures. But the 70% of them are compact with a mean radius of 30 astronomical units, and they don't show rings and they don't show gaps. We don't know if they don't show rings because they are optically thick or because they are very small and we cannot resolve. We don't have enough angular resolution. But they don't. Some of them are. We have enough angular resolution, and they don't usually show substructures. And these are the most common. And this is, in this plot, you can see the mass of the dust in the disk with the radius of the disk. And you can see in colors are the structure disk. The disk we show substructures, and these are the compact disk. And what you see is that when you have more, the structure disks are those with large radius and a lot of mass. So this is interpreted like a proof that substructures maintain the dust. If you, for some reason, have substructure, you maintain all the dust does not suffer too much radial drift, and you can maintain a big disk with a lot of mass. And in the compact, doesn't happen this. There is nothing that stops the migration. So you have a very compact disk, and you lose a lot of dust mass because it goes to the protostar. And this other thing is that these authors compare the rates of several correlations they see in this disk. And what they conclude is that the large disks with substructures are actually the precursors of planetary system we have already seen with very massive exoplanets. So what they propose is two evolutionary paths, different planetary systems, which are going to result in different planetary systems. You have an initial disk. If you have early formation of giant planet for some mechanism, we don't know. If you have a formation of large planet, you will create pressure bands, and you will have a large unstructured disk like this, and then at the end you will be able to form small rocky planets in the rings. If you don't have a massive planet at the beginning, you will end with a very compact disk, and maybe you can form small rocky planets at the end in the rings formed by the island. So you will have two different protoplanetary systems possible, depending on the initial or no formation of this. And this is something we are actually studying. We are looking at these two. We have looked a lot at HL tau, and now we are looking to DigiTau. DigiTau is very similar to HL tau. It's a nearby star, and it's very similar in mass, in age, and they are in the same region, but they are very different. DigiTau is very compact; it's only 50 astronomical units, and HL tau is 100 astronomical units. And DigiTau has no clear substructure, so they look like very good examples of these two evolutionary paths I mentioned earlier. And they are very young. They are 1 million years. So we are like studying two disks which has just entered one of the two evolutionary paths. So we observe DigiTau. This is a ALMA 1.3 millimeter, and we observe with the VLA, and we detected dust emission from them. It's very compact, so most of the dust is accumulated at the center, but actually you also have emission here, which is not easy to see here, but you can see when you obtain radial profiles. This is the radial profile. This is radio and brightness temperature for the 1.3 millimeter, the black solid line. This line is the dust temperature calculated, estimated from theoretical models. And what you can see is that when you look, you actually have some substructures at the 1.3 millimeters. When you look at 7 millimeter and 9 millimeter with the VLA, what you see is that you actually detect these rings and gaps when you look at the wavelength. So this means that this disk is actually having substructures, but you cannot see them because it's optically thicker than HL tau. So maybe this is something we are trying to answer. Maybe you have in the compact disk, you have the same mass, but in a much smaller disk size. And this will give more compact disk, but also more denser disk. And here we also look at a correlation between ice lines and substructures, but this is very difficult right now because you have to you need to have a very good determination of the temperature, and this is very, very difficult. So the last things I wanted to talk, and I think I am in time, is that polarization and observations. And this is the actual reason I am here today. And I am here in these weeks working at the because that polarization observation, which is something which have that polarization observation in protoplanetary is something which has become possible with ALMA, have revealed us that we actually don't know anything about the dust. So polarization mechanism and millimeter wavelength, and there are several mechanisms that polarize emission from dust, but there are two main mechanisms at millimeter wavelength that polarize dust emission. The first one is just simple thermal emission. Dust is not spherical in the protoplanetary disk. They are supposed to be elongated. We have evidence that the dust is elongated, and when they are elongated, they emit millimeter light, but is intrinsically polarized according to the elongation of the dust. So if you are looking at the thermal emission directly of the dust, you will see that there is an intrinsic polarization. There is another mechanism which we have learned very recently that is very important, is dust self-scattering. You have several dust grains in the disk. All of them emit thermal emission, polarized or not. Anyway, at some point, the light will find another dust and will scatter, and an observer here will see a scattering millimeter emission, which is linearly polarized, perpendicular to the direction of the light. So these are the two mechanisms, and we expect from millimeter emission when we see protoplanetary disk. We observe this. Of course, Escher Tau was the first object we observed with high resolution, mid-resolution here, polarization. And this is at 1.3 millimeter. This is with Karman. And you can see this polarization pattern, linear polarization, parallel to the minor axis of the disk. And this is exactly what we expect when the polarization is dominated by dust self-scattering, dust grains which are emitting, and they are scattered by other grains. And when you observe at 3.1 millimeter, you see a very different pattern, which is circular. So the only way to explain this pattern is because we have here dust thermal emission by elongated particles, which is intrinsically polarized, but all the particles, or most of the particles, are well aligned around the orbit of the disk. We still don't know how they are aligned, but this is the only way to explain this polarization pattern. So here, at 1 millimeter, when the emission is optically thick and you are dominated by scattering, you see the dust self-scattering. And when at 3 millimeter, when the emission is optically thinner, you see directly the thermal emission from the dust grains. So Kimasa Kataoka, which is a Japanese researcher, they proposed in 2015 to use the properties of the albedo and the dust self-scattering to get some more information about the dust size of the size of the dust. So here, what you are looking is this is A is the radius of the particle, so 2PA is over lambda is what is called the size parameter. So this is the size, something related to the size or to the area of the particle in relation with the wavelength you are observing. And this is the polarization. So when you have a small particle compared with the wavelength you are observing, if the light is scattered, you will have a lot of polarization. When the particle is similar to the wavelength you are observing, you will start to have less polarization. So when the particle is very large compared with the wavelength, you expect to have very low polarization. But this is if you scatter the light, but you have also a probability of scattering, which is how you can consider the albedo. So the albedo is different. You have, for small particles, you have very low probability to scatter the light if the light, for small particles compared to the wavelength. And you have more probability when you have a big particle compared with the wavelength. So actually, you have a very small region when the particle is similar to the wavelength, when you will have a probably when you will have lightly polarized, lightly scattered light, which is polarized. So you can use this to put constraints on the size, because this is now maximum grain size, and this is the P times the albedo. So if you set a one wavelength, you expect maximum polarization when you have a particle size which is comparable to the wavelength you're observing. So if you get the polarization, that's self-polarization at one wavelength, you can say you can have a good estimation of the size of the particle. And we did this. So this is the same I showed before. So you have at 1.3 millimeter, you have dust surface scattering. You don't have dust surface scattering at 3.1 millimeter. So you put this results in this plot, and you have 100 microns for HL tau. This is the maximum particle size in HL tau, 100 micron. And you do this for other of these, and you have similar numbers, 150, 70 microns. And this is a problem. This is a problem because I said a different thing. In HL tau, in the same disk, I said that we have pebbles, we have something which millimeter sizes, and you form planets from this. And from polarization, you get 100 microns in the same disk with similar wavelengths. And this means that at 1 million years, you still need to grow the dust by a factor of 10 in order to start to form planets, to start to form planetesimals. And both formalists are correct, and they should give the same. And this is very different. So here is a problem. We have been discussing this for several years now, and we have tried different ways to explain this, but we have always about the most evident solution, which is dust is porous. Dust are not spheres. Dust is porous. This is what you expect from grain growth models. They predict fractals, and they predict highly porous dust grains. And highly porous dust grain has a very, very different optical properties, especially when the wavelength you are observing is similar to the size of the dust grains. You expect very different things, and this means that you are what you are getting from the dust continuum or from the polarization is very different from reality. This is what we have seen in comets. This is a work by Olga Munoz, and in 2020, I don't remember the comet here. So these are observations of the phase function in the polarization at different phase angles in the coma of the comet, right? So this is the dust, and the comet is supposed to have dust from the protoplanetary solar disk. So this is like a picture of the dust in the young protoplanetary disk in the solar system. They found that the only way to explain this is with this, which is dirty cotton, actually. They measured in the laboratory cotton, which is simulating a particle with very high porosity, and dirty, this means with carbon, right? This is because it's very, it's highly absorbing, highly porous particle. So this is the only way to explain the observations of comets in the solar system. So this means that the young protoplanetary solar disk has a very highly porous dust particles. And we recently have measured this in this actually. In some disks, here you have a different way of polarization. It's the central star is emitting in infrared. So you have different scattering angles here when you can observe this. So you can obtain the phase function of the disk and study the properties of the dust, which is in the atmosphere of the disk. And what they saw when they observed a sample of protoplanetary disk is that they found two different behaviors of the phase function, category 1, category 2. These are decreasing, and this has like a maximum and then a decrease. And these are very different, and category 1 is explained only by high porosity fractals. And category 2, is explained by low porosity or moderate porosity, like 70%. So this means that the particles, which are small particles coupled with the gas at the atmosphere, at the surface of the disk, are already porous particles, and you can measure that. So, and this particle is what are going to form the bigger particles, the millimeter and centimeter particles we are observing with ALMA. So, the most probable situation is that we actually are seeing the emission from porous particles, something like this or something like that. And this is very different from spherical particles, which is what we are using right now. Indeed, we studied this last year from a theoretical point of view. We use some approximations. It's very difficult to measure, to calculate the true optical properties, but we made some approximation, and this is what I showed. This is the wavelength, the expected polarization at different wavelengths for from different particles when you have a sphere, and this is what I mentioned. You have polarization only at one wavelength or a small wavelength range around one wavelength. When you consider porosity, what you have is this is the maximum. This is highly porous grain. You have from a single dust grain, you have polarization at very different wavelengths. So you can explain polarization at different wavelengths from a particle with a size which is very different from this wavelength. So this is the only way to reconcile the results from the study of the spectral energy distribution and from the polarization in this. In the case of HL tau, in this work, we put a constraint of 70 or 97% of porosity, which is moderate. It's not a fractal. It's something more similar to a volcanic rock. But actually, we did this in HL tau. We obtained a lot of observation of HL tau, different wavelengths. This is from 7 millimeters from VLA. And you can see here a circular pattern at 3 millimeters. And the pattern is changing as you go to higher frequencies. At the end, at the higher frequency, you have the pattern of polarization vectors parallel to the minor axis of the disk. So this is dominated by dust self-scattering, and this is dominated by aligned grains, the thermal emission from aligned grains. And actually, at each wavelength, you have both mechanisms. And you and if you model this, you can obtain the relative contribution of both mechanisms. So you have here, this is the polarization, and this is the wavelength, and this is for the thermal emission directly from the intrinsically polarized dust grains, and this is from dust self-scattering. And what you can see here is the same with different resolution. What you can see here is that actually dust self-scattering is not at one single wavelength. You have dust self-scattering a similar polarization of around 1% at all wavelengths. So this is only all this behavior is only consistent with moderately porous, elongated, and aligned particles in the orbit. So this is clear now that we have porous particles, and this changed everything. If you have porous dust grains instead of compact spherical dust grains, particles are going to be larger than you are measuring. In the case of HL tau, we estimate like 10 centimeters, and the dust mass is larger. Not only that the dust mass, all the dust is stored in optically thin regions, and you cannot estimate well then. Sorry. Also, if you consider if you consider that they are porous, this means that you have 6 times larger dust mass in the disk. The problem is that we need to use opacities calculated for realistic porous particles. There are not opacities calculated for realistic porous particles. So we are still using spherical compact dust grains in order to obtain the dust property. And this is the reason I am here. This is the PhD project of Gonzalo Vargas, who's there. Who started a project recently thanks to the Severo Shoah program, and is co-advised by Daniel Guirado and me. And this is a real calculation he made this week. This is a particle, a fractal particle he created, and he managed to calculate all the scattering matrix properties. So we can, the project is to measure this for different wavelengths and different sizes and different porosities. We are gonna measure fractals and also very compact sources, but with holes. So we create the porosity, and we're gonna obtain this and make tables you can insert in radiative transfer modeling, and then model correctly the dust emission at different wavelengths in protoplanetary disk. So this is my summary, but this is not the end. So the first thing I said is that ALMA has a lot to detailed studies of particle distribution in this. We saw extended, very large disk with 100 of astronomical units rings, and the most important characteristic is gaps and rings. And rings are excellent places to form new planetesimals. Now we know that most of the disks are compact, actually. So we have like two different kinds of disks: large with substructures, compact with no substructure. We don't know if they have or not. And we think that these are two evolutionary paths, and they will end in very different planetary systems, one with massive big planets that are formed very early in their evolution, and the other with only rocky small planets. And the polarization is revealing that we don't know anything about the internal structure of the disk, of the dust, sorry, and this has strong implications where probably dust in protoplanetary disk is not spherical, they are elongated and aligned, and they are fractal or porous dust particle, and this is gonna change all the physical parameters we are measuring. Last thing I want to talk is the next generation VLA. The next generation VLA is gonna be the biggest machine built by the human people. It's gonna be an interferometer, which is it will have almost 300 antennas distributed by all North America. We will have it's going to be centered in New Mexico, in Socorro, and we'll have antennas also in Texas, Arizona, and the north of Mexico. Yes, Mexico is North America, and we have antennas also in Canada and the rest of the United States, Hawaii, and the Puerto Rico. This big interferometer is going to have 10 times higher sensitivity and 10 times higher angular resolution than the VLA and ALMA, and it's going to observe in a wavelength range very similar to these two interferometers. It will go from 20 centimeters, I think, 1 gigahertz, to 3 millimeters, 3 or 2 millimeters. So it's the first time we will be able to observe thermal emission, dust thermal emission at resolutions of 1 milliarc seconds from this. And this is a simulation. This is HL tau, actually. This is ALMA, 1 millimeter. You know, is optically thick emission. If you want to observe optically thin emission, you need to go to the VLA, but you cannot observe this here at the center, where you expect the formation of rocky planets, because it's optically thick. Because you don't have the enough angular resolution. This will be solved by the next generation VLA, and actually protoplanetary is, and the formation of solar system analogs is the first key science in the next generation VLA, but it's going to solve a lot of problems. And this is my last slide. Thank you very much.
Okay, thank you, Sammy, for this very nice talk. It's time for questions.
It was very interesting for me. I don't have this kind of background, but it was very interesting to see this talk. This might be a very naive question, but in the beginning of your talk, we were explaining how the bigger dust particles move and form this regions of dark and light regions.
Oh yeah, I cannot hear you very well.
Okay. I'll just now I get.
Okay.
So I was saying that these regions of bright and dark bands that you were seeing, I could understand the mechanism why the particles would move towards the inside. Like, is there any angular momentum that would make these particles go outside? What is the driving force that actually makes this particle? Is it just gravity? What is the driving force that makes this particle go inwards rather than outwards? to form this collective bands near the.
Okay, in the rings. You mean why they don't move inside? Because they follow. They goes to the higher pressure. So actually, the rings are created in the higher in the gas. If you see this.
Yeah, it was at the very beginning.
This is a simulation of what happens when you have an accreting protoplanet, and this is the gas. This is the density of the gas. So you create. It's like the planet is moving, is evacuating the gas from its orbit. So it pushes the gas to the edges. So you have more gas in the edges, and you have higher pressure of the gas there. So the dust grain only follows to this. Only follows the gas. And it's independent, actually. You can do this with several mechanisms, but it's much more easy with a planet. But you don't need a planet. And it's always the same. You need to create pressure bumps.
Hello, Carlos. Thank you very much for the nice talk. I have two questions, if there is time. One related to the disks. I wonder what is your thought, or what are your thoughts on massive protostars, which also have disks, right? Will all this talk not apply at all, or will all the snow line move forward, which I think is going to happen? But I wonder what your thoughts are on the dust distribution, the gas, and even planets, because I think there are not that many planets around massive star, meaning more than 8 solar masses for.
We don't know, and we actually want to see. I mean, it will be very nice to see, and probably you need the next generation VLA also for this, because massive disks are very far, so it's much more difficult to resolve the structure of the massive disk. There are not a lot of them known, and you don't know. I mean, massive disks are thought to be more turbulent, more big, massive, and it's more info. It's not. Maybe they are not as ordered as this T-Tauri star, right? But we don't actually know. And you have another problem. Maybe you form planets, but at the end they are destroyed because when the star when the star has born, it started a lot of radiation, and we don't know if it destroys everything or not. And it's a very interesting system to look at, I think. There are some studies from ALMA, but it's very optically thick, the emission, even at the long wavelength, so we still don't know.
And about the dust, you mentioned that, for example, Olga's work in the comet measure the dust properties and stuff, and I wonder if the dust property has not changed at all in 4 billion years. Like, do they stay the same as in the primordial protoplanetary system? Because 4 billion years.
I don't know anything about it. But what I think is that they store dust from a given age in the protoplanetary disk, right? So if you see a comet which is coming from the outside of what you see is that the dust in the initial stages of the formation of the planets in the solar system, if they were already porous, I mean, you form planets from this. So all the dust should be porous. I'm not sure if they are fractals. I mean, measurements of these in comets and measurement of dust in the atmosphere of the protoplanetary disk say that they are fractals, which a lot of with very high porosity. But I don't think this is the case for the millimeter and centimeter particles we are looking at the millimeter and centimeter, because you need to grow this by shocks. So at the end, it will compact at some point, right? So actually, in initial tau, at millimeter, we say that it's more or less 80% porosity, and this is very different from a fractal. This is more similar to this. So this is why we are going to calculate both cases, which are very different.
Thank you, Carlos. This is a question coming from my complete ignorance on the subject. So, do you think that the square kilometer array, so SKA, is going to give us some other clues, or what kind of different approaches do you expect from that?
I didn't show a image of a protoplanetary disk with the SKA, and there is. And I was the referee of that paper. Yes, in principle, the SKA has the ability to detect dust emission at 6 centimeters, which is very good because at 6 centimeters you will see the most of the thermal emission emitted by particles of 1 centimeter should be emitted at 6 centimeters. And the SKA has the sensitivity and has the angular resolution to observe dust in a protoplanetary disk. And there are simulations of that, and there are papers published about that. And this is very bad. I didn't show it. But you need a lot of time actually, because it's very weak. At 6 centimeters, it's very weak. And in that paper, they estimated like 1,000 hours of SKA to obtain a good image. I mean, an ALMA-like image of the dust in a protoplanetary disk. But with 100 hours, you can make studies of the radial distribution. Only with 100 hours. But there is a problem they don't discuss, and it is the free emission. When you go to longer wavelengths, you start to have a lot of free emission from winds or from evaporated gas. And this is a problem they still don't know how to solve, but they are working on a way to separate both contributions.
Hi, Carlos. Thank you for your nice talk. Before your polarization section, you showed several radial profiles of the emission in digital. What I noticed is that near the center, the brightness temperature is higher than the dust temperature.
Because this is
How do you explain that?
This is for free emission. What is happening here, you cannot trust it's not dust anymore. It's dominated by free emission from the jet. Digital has a very strong jet. And in principle, these observations were designed to subtract the free emission at the center, but it's very difficult. This is something very difficult, and what we know is that a free emission is only present here. So here, we know that we are dominated by dust emission. So to study this is enough.
And that line of dust temperature, how is it?
No, this is theoretical from, this is simply, this is the dust temperature you expect from a disk around a star with this luminosity, but flare disk. You can play a little bit with the flare, but it's very stable. I mean, it's not very different if you play with it. And what we have seen is that it's very close to what we measure in some disks.
The last question, is there an easy way to explain to non-experts why is there preferential orientation of the polarization in the case of self-scattering instead of having something?
That's self-scattering?
Yeah.
Okay. You mean this?
Yeah.
Yes, because so I said this, but you have a dust grain and emits and finds another. Okay, but you have also here. So you have everywhere dust grains. So at the end, you cancel the polarization because you have emission coming from all directions, right? So in principle, if you have a dust grain in the middle of a protoplanetary disk, you should not see polarization, unless that you have more dust in one direction than in the other. So in a phase on this, you don't expect polarization by dust self-scattering. But if you have a slightly inclined disk, you will have more light coming from the both sides than from the other side. So you expect this to have more light coming from here in this direction than from here. So you will see like a residual polarization in that direction. And this is one of the reasons why it's so small, that polarization, the polarization degree is around 1% only.
More questions? More questions? No. Sorry, no, first, let's thank you, Charlie. Remember that Shirley will stay here until when? Are you
Until tomorrow,
tomorrow already? Okay, but this afternoon they are organizing.
we have a
a
long
meeting
meeting. Yeah.
for everyone about that in general, so it will be, Nani, it will be what time for?
And the sala de juntas, so we will have a Zoom room for anyone that needs to do it from home.
Okay,
Thank you.
that's all.
Esta es la misma para de cuando me